Hi, my name is Madhav, and today I'll be talking about queues, fairness, and the Go scheduler as a whole. So, a little bit about me before we get started. I work at VMware, where I work on open source Kubernetes full time, because of which I spend most of my time in the community there, working mainly on areas of API machinery, contributor experience, and architecture. Currently, I am also an undergrad at PS University, Bangalore, India. So, let's get started. Now, the agenda for today is as follows. We'll start with a little bit of motivation, talking about why we are here and why do we even care about this. Then we'll talk a little bit about the Go scheduler model. We'll talk a little bit about fairness, the design of the Go scheduler, and then actually visualizing what's happening internally by pulling out some metrics and playing around with things. Then we look at one of my favorite topics, which is looking at the fine print of things, that is really going deep and looking at what's happening under the hood there. We'll look at what some of the knobs are that the runtime provides us with that we can play with. And finally, I will leave you with a few references and materials that I found particularly helpful to understand these topics better. So before we get started, a small disclaimer. Everything discussed here is in reference to Go 1.17.2, which was the latest Go version as of this recording. So why are we here and why do we care? We are mainly here because we love Go's concurrency primitives, namely Goroutines and channels. Let's talk about Goroutines mainly today. So Goroutines, it's really helpful to think of them as lightweight threads, which are managed by the Go runtime, and you have a super minimal and easy to use API to work with them, which is namely the keyword Go. So you can do Go func or Go function name or whatever to create a Go routine and run things and utilize concurrency. Now, let's take a small example. Let's say this is our program. We have a main function and then we create a Go routine to go do something, and we call another function to do another thing. Let's look at this particular code snippet. We have a main function which creates a Go routine, call another function to go do another thing. Now let's actually compile this into a binary called app. Another way to look at this binary is having two logical parts to it. One being our application code itself, and the other being the Go runtime. Now, our application code often calls into the Go runtime to help with things such as creation of Go routines, executing system calls, allocating memory, and so on. So, an example of what calling into the runtime looks like is something as follows. When we compile this program, it actually gets compiled. The statement go do something actually gets compiled to a runtime function called new proc, which is responsible for creating a new Go routine. So this is just one small example of what it means for our code to call into the runtime. And then we have our operating system, which is responsible for actually running our code. The runtime is what interacts and interfaces with the operating system to handle things such as creation of threads, actual operating system threads, if it needs to, as we will see, and handling memory and so on. Now let's actually run our code. So when we run our code, we have multiple Go routines that might exist at any point of time. But it's also important to remember that these Go routines exist in the user space. Now, subsequently, in the kernel space, you also have OS threads or operating system threads that exist. And then finally, you have the actual hardware on which our code actually runs on. Any actual execution happens through running operating system threads onto hardware. And at most, you can run the number of operating system threads that you can run is equal to the number of hardware cores that you have. So in this case, it's four, and you can have more number of operating system threads than hardware cores available, and subsequently you can have more number of Go routines than operating system threads available. Now, how do we get the code inside Go routines to actually run on the hardware? That is, we need some way to map Go routines to operating system threads so that they can be run on our hardware. Now, this is what is known as user space scheduling. There are multiple ways to do user space scheduling, but we will look at the one which Go follows. There is another excellent talk by Kavya Joshi on the Go scheduler, which discusses three ways to do user space scheduling in great detail, along with pros and cons. So I'd highly recommend checking that out as well. I've linked that talk towards the end. So what Go follows is something known as NM scheduling. What the NM scheduling model gives us is it gives us increased flexibility, more importantly. And what this basically means is that you can have substantially more number of Goroutines than operating system threads that exist at any point. And these Goroutines are then mapped on, are then multiplexed onto different OS threads. And the advantage that this gives us is if a Goroutine is suppose running on an OS thread and makes a blocking system call, for example, then then that operating system thread is also going to block. And if there are other Goroutines that are meant to run on this blocked thread, those would also block if nothing is done about it. What this model allows us to do further is it allows us to take this other Goroutine which was supposed to run on this thread and make it run somewhere else, as we will soon see in much greater detail later on. So as we saw, the Go scheduler does NM scheduling. And the next question that comes to mind is how do we actually keep track of Goroutines that are yet to be run? So at any point, your program might be creating more and more Goroutines to run, but how does the user space scheduler that exists actually know what Goroutines it has to next run? Following how the OS scheduler or the kernel scheduler does things, we could have a run queue here. So let's maintain a global run queue of Goroutines that are yet to be run. And this queue follows FIFO first in, first out. Now, the first important thing to note here is that with FIFO, there comes an inherent notion of fairness, meaning that if a Goroutine is created first, it's only fair that it gets to run first. And subsequently, the operating system threads that exist can take Goroutines from this global run queue and then run them, or the user space scheduler can explicitly go ahead and assign Goroutines to different operating system threads to run depending on how it's implemented. With this state, there are a few things that are worth discussing and taking into consideration. Since we have multiple OS threads accessing the same shared data structure, which is the global run queue in this case, we would need some way to synchronize access there. And a lock is one way to do it. And that's how the initial Go scheduler did it as well. That is Go 1.0. This is how things happened back then. Now, if you have a lock which needs to be acquired and released every time a thread needs to pick a Go routine, things won't be as scalable as you might want them to be. Mainly because if your Go routine is, for example, short running, and let's say the Go routine finishes running, the operating system thread would need to get a new Go routine. If it needs to get a new Go routine, it needs to acquire a lock, wait for a lock if it's not available, and so on. So there's going to be a lot of contention here. So things aren't going to be scalable. Now, what if the running Go routines happen to be in long running tight loops? It's likely that the ones in the run queue are going to end up starving. And one way to deal with this is actually forcefully stopping the long running Go routines and making them execute later on, also known as preemption, which we will talk in greater detail later on. Uh, so once you actually try and preempt something, what's going to end up happening is that you need to decide what length of time slice is appropriate for each Go routine. Now, if you keep a shorter length for each Go routine, what's going to end up happening is you're going to have more timely access to the shared resource, but also you're going to end up with a lot of context switching that's going to occur. So from a fairness point of view, and from an efficiency point of view, this is not going to be the best way to go about it. So to mitigate these issues and challenges, what ended up happening was as follows. The notion of distributed run queues was introduced. So each OS thread would have its own local run queue that it would have a set of Go routines that it could take from and run. The advantage here is that for the OS thread to access the run queue, it does not need to hold a lock because no other entity would access this particular run queue then. There is still a global run queue maintained to keep track of Go routines, the reason for which we will soon see. Since there is a global run queue, you're going to have a lock there. But the contention problem here is substantially reduced because each OS thread is going to be taking things from its local run queue more often than it's going to be taking things from its global run queue. And as of Go 1.17.2, and this has been the case for quite a while now, each local run queue has a dedicated length of 256 Go routines. Now, that looks good so far. But let's take a small detour and talk a little bit about what GoMax prox is and what it actually means for us. So, GoMax prox, according to the documentation, the way it's defined is as follows. It limits the number of threads that are actually executing and actively running code. The meaning of this is that if there are threads that are blocked in system calls or threads that are blocked otherwise, those threads are not going to be counted against the go max prox limit. And what this subsequently means is that you can have a large number of threads that are going to be blocked in syscalls, but only a small number of threads that are actually executing code. Another thing is that we maintain per thread state here, namely one of the per thread state being we maintain local run queues. Now, if a thread is blocked in system calls, it does not really need to maintain a local run queue. And subsequently, whatever go routines are part of that thread and are blocked, and that thread is blocked in system call, those go routines will probably be used elsewhere and run elsewhere. So we don't need to maintain that per thread state. It's not too efficient from a memory standpoint, as well as those go routines could be better utilized elsewhere. Second thing is that the Go scheduler is what is known as a work stealing scheduler, as we will soon see. Meaning that if a particular thread does not have work to do, it's going to try and steal work from other threads that have an excess of work that it is currently doing. So in order to try and steal work, it would then now each thread would have to check with an unbounded number of operating system threads. And this again is not as efficient and scalable as we would want it to be. So how do we tackle this? To deal with this, the notion of something known as a processor was introduced. Processor, like the Goroutine and the operating system constructs, is also a heap allocated data structure. A processor is actively executing Go code and has an OS thread that is associated with it. And much of the state of the previously per thread can now be moved into the processor named such as the local run queue. So now you have a bounded number of entities that you would have to check if you have to steal things or you have to steal work rather. And another thing is that the number of processors is always going to be equal to the number of Go max procs that exist. So this is what our scheduler now looks like from a very high level. You have a global run queue with a set of Goroutines, which is behind a lock. And then you have a set of processors whose numbers are equivalent to the value of Gomax procs. And each processor has a local run queue with a bunch of Goroutines. And you have an OS thread, which actually is executing some code. For more detail into the design decisions of this and why things happen the way that it did, this particular talk by Dimitri Vyuko, who is also the original author of the new scheduler design, which is the new and improved scalable Go scheduler. This talk is an excellent watch for that. So if you're interested, please check this out as well. Before moving on, let's actually spend a minute or two talking about fairness in general. So, what do we mean by fairness and why do we care about it? So, let's consider the following scenario. Let's say we are at a supermarket where there is a cashier helping us checking out things, and you have a bunch of customers waiting in line to get their items processed. And each of these customers can have a bunch of items that they want to check out. And this queue is FIFO again, first in, first out. This looks fine. But what if the scenario is something as follows? Let's say one of the customers that is the first customer has an excessive number of items being processed. So here it's shown as 6, but it could be, let's say, 20, 25. What's going to end up happening is that the cashier, which is the resource that these particular customers actually want, is going to end up spending most of its time on this one customer, and the rest of the customers behind this one customer are going to end up starved of this particular resource. So in scheduling, especially in presence of a system which is FIFO, if you have a resource hog, so the first customer there, it leads to something known as the convoy effect happening. And this is a common problem that happens in scheduling, and there are multiple ways to deal with this. So, how do we deal with this in scheduling? One way is to just schedule the shorter running tasks, but this would require us to know what the characteristic of the workload actually looks like. And this isn't always the case, and sometimes it's not even possible to know this. Another way to deal with this is something known as preemption. Now, there are two types of preemptions called cooperative preemption and non cooperative preemption. In cooperative preemption, what ends up happening is you end up trusting the entity that it is going to give up the resource voluntarily in a timely manner. But if it doesn't end up doing so, there is pretty much nothing that you can do about it. That is cooperative preemption. Non cooperative preemption, on the other hand, says that, hey, you know what? If you've been running or consuming this resource for a certain amount of time, after that time, you are forcefully going to be stopped whether you like it or not and run at a later point of time for your remaining duration. What this allows us to do is it allows us to give the other waiting entities some time on the resource as well. Now, keeping these two in mind, let's move on and find and again revisit the concept of preemption from the Go scheduler's point of view at a later point. So, all right, now that we have enough context, the first thing that we ask ourselves is, how do we even choose what Go routines to run? We have so many Go routines. We have in our local run queues, we have in our global run queues. So, which one do we actually end up running? So, let's try and understand that first. Let's say that the Go routine that is currently running, as highlighted here, ends up calling into the runtime through some way and exits and stops execution. Now, this particular processor is not going to have anything to run, and it needs to choose one Go routine that it can run. Remember that an initial issue was that we were checking the global run queue with a lot of lock contention, and that led to issues. So what we end up doing is, first we check the local run queue, for which we don't need to hold any such contended lock. So we check the global run queue if it has work available, work in terms of Go routines. So here, yes, we do have work available. So we take a Go routine from there and we start running it. Awesome, that works great. Now let's say that the local run queue of processor P0 is also empty. What do we end up doing now? What we end up doing now is as follows. Now we actually check the global run queue next. So we hold the lock, we check if it has work available. If it does have work available, we steal from the global run queue and then start running those Go routines. But there are multiple reasons as to why we steal from the global run queue first, rather than checking some other source of work. So we check the global run queue. It has work, and now what it's going to do is, it's not going to take just one Go routine and run it. Is what it's going to do is, it's going to take the number of that is equivalent to the length of the run queue divided by the number of processes that exist. So it tries to take what it thinks is its share. And what this also allows next is, if some other processor wants to check the global run queue for work, it would then find the number of Go routines equivalent to its share also available there for it to steal. And if you steal multiple at a time, you don't need to further keep checking the global run queue often, and you further reduce the problem of lock contention there. So you check there is work available, so you steal the proportional number, and you get Go routines now in your local run queue. So now you have things in your local run queue, you start running it from there. Now, what if the global run queue also is empty? What do you end up doing then? Next, what happens is, there is another component in the runtime known as the netpolar, which is responsible for handling asynchronous system calls, mainly network I/O. So if a particular Go routine is waiting on a network I/O system call to return or get a response back, is going to end up waiting on the netpolar rather than blocking an actual OS thread. So this asynchronous type of blocking is extremely helpful in the runtime, and this is what also happens in the cases of blocking on channels or timers as well. So next, what we're going to end up checking is the netpolar. If the netpolar has any work. So let's say that the netpolar has a ready Go routine. So it takes the Go routine from the netpolar and starts executing it. But what if the netpolar is also empty? What ends up happening then? So here is where uh, the processor ends up stealing work from another processor. And this is what we talked about earlier when we said that if you have to check an unbounded number of OS threads, things would not become as efficient as you would want them to be. So here we have a bounded number of processors, which is two. In this case, it calls into the runtime. We need to find some work. Local run queue is empty. Global run queue is empty. Netpolar is not giving us any work. So now we end up stealing half of the work available in another processor. So in implementation, what ends up happening is, the processor randomly picks another processor and then checks if that processor has work available. If it does, it steals half of it. Now, since we are randomly picking things, it's also possible that you might end up picking yourself, and stealing from yourself when you don't have any work doesn't really make sense. Or you might end up picking a processor that um, also doesn't have any work. This process of stealing is retried actually, and I think currently it's retried 4 times. So it steals half the work that is available from P1 and it brings it in its local run queue. Now, since there's work available in the local run queue, it picks things from the local run queue and starts running. Awesome. So that looks good. But there is still the issue standing of about the convoy effect. What will that be taken care of in the current scenario? We spoke about preemption earlier. Now, actually, let's see how Go does it. Let's look at the history of preemption in Go. So, in Go 1.0, you had purely cooperative preemption, meaning that if you had a tight loop or a hot loop that ran, let's say, infinitely or for a really long period of time, and it did something, what's going to end up happening is that that goroutine is never going to give up the processor, and all the other goroutines are going to end up starving then. Or if not starving, you would have increased latencies there. In Go 1.2, what was introduced was function call preemption. Here, what happens is whenever a function call is made, there is a check to see if the stack size of the goroutine needs to grow, and that check is subsequently responsible for handling preemption of that particular goroutine if needed. But the problem here is that that function call might not happen at all because the compiler might just inline that particular function for efficiency reasons. And if that function is inline and there's no actual function call taking place, the same issue as the first case happens. But in Go 1.14, what was introduced was non-cooperative preemption or asynchronous preemption, meaning that if a Go routine ends up running for a certain amount of time, regardless of whether it makes a function call or not, it will be preempted eventually. Now, each Go routine is given a time slice of 10 milliseconds, after which a preemption request is issued. This 10 milliseconds is again a soft limit, and preemption is actually issued by sending a user space a signal called sigurg to the thread that is actually executing the Go routine. Now, to understand more about why sigurg and what the design process behind this particular feature was, there is a talk detailing out this particular change by Austin Clemens in a previous GopherCon. So, who actually ends up sending this particular signal, and from where does it come? So there is a long-running daemon in the Go runtime called sysmon. So this particular Go routine is long-running and it does not execute on a P, or in other words, it executes without a processor, mainly because this particular Go routine handles a bunch of other stuff in the runtime. Uh, Two cases of which we will soon see. So the first case being it helps with preemption. So if it sees that a Go routine is running for a long period of time, namely it's ran for 10 milliseconds, it issues the preemption signal. So let's see what that looks like. So if a Go routine has been running for 10 milliseconds, the sysmon daemon sends sigurg to the thread that is actually running the Go routine. So where does this preempted Go routine end up going? Let's say that the Go routine ends up running in an infinite loop. What's going to end up happening is after 10 milliseconds, you preempt it. If you put it back in the local run queue, and all of the Go routines in the local run queue now are, let's say, short lived Go routines or that do some work, for example, well under 10 milliseconds, what's going to end up happening is that the Go routine that you ended up preempting, let's say you put it back in the local run queue, these Go routines run, that particular Go routine starts again, it's going to run for 10 milliseconds, and those other Go routines, which are actually very short lived, will end up having to wait for an entire 10 milliseconds slice. So effectively, what is done is once a Go routine is preempted because of it being long running, it's going to be put back in the global run queue, effectively meaning it's going to be run after everyone else. Let's try and observe what's actually happening when we are running something. So let's try and pull out some metrics from the Go runtime. And also, since the preemption is issued using a user space signal, we can actually use the Linux kernel's tracing subsystem to observe that these signals are actually being sent. So let's see what that looks like and try and understand things in a better manner. To see what's happening inside the scheduler, what I've done is I've written a small tool which takes the scheduler traces that the Go runtime provides us with and exports them out to Prometheus for us to visualize. Now, for the purposes of this demo, I'll be setting the value of GoMax prox to 2, mainly because it's easier to visualize things that way, but the same interpretation and results can be extrapolated to higher values of GoMax prox as well. The way we're going to do this is that first we have a configuration file that we will provide to this tool, and it's as follows. So we have a path which specifies what the value of gomax prox is, which is 2 for us, and then subsequently what binary we want to run. And then we give it a bunch of Prometheus configuration as well in terms of what endpoint should it scrape metrics from and what the port should be. And the interval here under shed indicates how frequently you want to get runtime traces from regarding the scheduler runtime traces out from the Go scheduler. So in this case, it's 10 milliseconds. The effective command that ends up being run is as follows: go debug equals schedtrace, which allows the Go runtime, or which enables the Go runtime to emit scheduler traces, and we do that at a period of 10 milliseconds. And then we set go max prox equals to, and that's our binary name. Now, before actually running things, let's look at the code that we're actually running the binary for. So the code is pretty simple. We spawn 10 Go routines, each of which does some CPU intensive work, and then we finally wait for them to complete. Now, the CPU intensive work function here is basically a function that multiplies two matrices of size 1024. It's nothing of significance, but it's just something to create long running workloads so that we can visualize what's happening inside the scheduler. So now to actually run this tool, before we run it, I'm going to start Prometheus as well. I've kept the scrape interval to be 10 milliseconds, mainly because that's the time slice for preemption for each Go routine, and things become significantly clearer when that's the scrape interval for Prometheus as well. So let's actually go ahead and run this. So now that our binary is running and we are starting to serve metrics, what we can then do is we can go to Grafana and go to our data source and just verify if everything is working correctly. Yes, it is. So our scrape interval is 10 milliseconds. Let's just save that. And now let's actually add metrics that we want. So we will we will add in local run queue 0, which is our first run queue length. And then let's add in the other two run queues as well, which is local run queue 1 and the global run queue. There you go. And add. Okay, awesome. So let's just zoom in here a little bit to see what's happening. So here we can see that we have three lines as we expected, and now the yellow line is local run queue 1, which is this line here. And then we have green line, which is the local run queue 0, and the blue line is our global run queue. So let's see what's actually happening here. So initially, local run queue 0 had three Go routines which were running, and local run queue 1 had two Go routines running. And as you can see here, after 10 milliseconds, one Go routine gets preempted, and as soon as it gets preempted, it gets put into the global run queue. So each of the local run queues, that is, each of the processors were running one Go routine which got preempted, because of which each of them had a dip by 1, and the global run queue effectively had a rise by 2. Now, if you see here at this point now, the local run queue 1 has pretty much no Go routines running. So it's going to check its local run queue. It has nothing. So what it does next is check the global run queue. Now at this point, the global run queue has 7 Go routines that were running. What ended up happening was it's the local P1 essentially stole 4 Go routines, and the number of Go routines for P1 became 4 here. Post which local run queue 0 also ended up stealing Go routines, because of which there was a further dip. And as you can see, next Go routines ended continuously end up getting preempted after 10 milliseconds, and the global run queue's length goes on increasing by 1 each 10 millisecond period. Post which, as soon as something reaches 0, uh, it steals work and the global run queue length drops, and then it keeps on going. So this is pretty much what we saw earlier, and it was really interesting for me to actually visualize this and see that what was actually happening inside. Now, another thing that we can actually observe is that whenever a preemption request is issued, that preemption request is issued using a user space signal called SIGORG, as we saw earlier. Now, since this is a user space signal, what we can then do is we can use Linux's um, tracing subsystem to actually get events for whenever that particular signal is issued, and thus enabling us to see the preemptions that actually happen while the program is running. So let's go ahead and stop this program. And to enable the whole tracing mechanism, I have a small script here which enables it. So let me go ahead and run this script, which enables filters and all of that. Now sig23 here. 23 is the signal code for SIGIRG, similarly to how 9 is the signal code for SIGKILL. So let me go to the tracing directory, which will have our log. And now let me run the binary itself. So this is running. Now if we do, if we look at the log and we grep for GopherCon, which is our binary's name, we will soon see that the GopherCon binary here, let me just zoom out a little. Yeah, the GopherCon binary here has a ton of preemption signals being issued um, at regular intervals of time, and these are basically the thread IDs to which the signal is being issued to. So this was also really interesting for me to see these signals being emitted and observing them as they happen. Okay, so now that we've seen what actually happens inside the scheduler, let's revisit our code snippet from what we just ran. So just to recap, we run 10 Go routines, each of them doing some CPU intensive work. The question that arises now is that when a Go routine spawns other Go routines, as in this case, where do these spawned Go routines end up going? And the answer for that is that these spawned Go routines are put in the local run queue of the processor that is responsible for spawning these Go routines. Considering FIFO brings fairness to the table, should we put the spawned Go routines at the tail of the queue following a purely FIFO approach, or can we do things in a better manner? So let's look at what a purely FIFO approach would look like. So this spawns another Go routine. This Go routine gets put at the tail of the queue. So there are a few interesting considerations here. Namely, FIFO is good for fairness, but it's also poor for locality. LIFO, on the other hand, that is last in first out, is great for locality, but it's bad for fairness. But maybe we can look at a few Go specific practices that we can look at and use to optimize for commonly used patterns. So channels are often used in conjunction with coroutines, namely for communication or synchronization. And let's look at the following code snippet to try and understand this better. So here we have two coroutines, a sender and a receiver, that are communicating over a channel. So the sender sends something on the channel, the receiver receives it and processes it. Now, this is an unbuffered channel, meaning that if the sender sends something but the receiver has not received it, the sender is going to block. But if the receiver, and subsequently, if the receiver tries to pull something out of the channel but there's nothing there, the receiver will block till the sender sends it. So let's try and illustrate this. So let's say the receiver is running, the receiver tries to receive something but it blocks. The sender is supposed to run next. So the sender runs, unblocks the receiver. Now, where does this receiver end up going? It ends up going at the tail of the queue following a purely FIFO approach. It would have to wait for all other Go routines effectively in the local run queue to actually be able to start processing that message. So what is the impact on performance here? Let's assume that all the Go routines in the local run queue are long running ones. So on an average, each of them are going to take 10 milliseconds to preempt. So if one of these, either the sender or the receiver, is at the tail of the queue, it's going to have to wait for, on the worst case, 255 into 10 milliseconds, because 256 is the length of our run queue. So can we? This essentially might be an issue of poor locality. So can we combine LIFO and FIFO approaches to try and achieve better performance in some form? So let's consider the LIFO approach. So as soon as a Go routine is spawned, you put it in the head. You put it at the head rather than at the tail. What effectively ends up happening is that these two coroutines can end up responding one another constantly, and then they can end up starving all of the other coroutines in the local run queue. To solve this problem, there is what Go uses is something known as time slice inheritance, meaning that whenever a Go routine is spawned, the spawned Go routine inherits the remaining time slice of the Go routine that spawned it. So in this case, this if a Goroutine spawns another one at the 3 millisecond mark, the spawned Goroutine gets a time slice of 7 milliseconds rather than 10 milliseconds. Now, this effectively ends up giving these two Goroutines a time slice of 10 milliseconds um, together in order to run, after which one of them will end up getting preempted and the other ones can continue execution. And the impact of performance on this was rather significant. From this snippet is taken from the commit that implemented this change, and there was a benchmark called benchmark ping pong hog, which is similar to the example you saw earlier with the sender and receiver. That benchmark improved by 99.88%, and not just this one benchmark, there were improvements throughout the language. This looks good, but you could still end up starving the go routines in the global run queue because you might never end up polling it. And the solution for this is that you poll the global run queue occasionally. How do we compute the condition in which that decides when to poll the global run queue? Meaning that firstly, it should be efficient to compute because this is in the scheduler's fast path. Secondly, while implementing this, a few things work initially considered. So first, it was made that the condition was a function of the length of the local run queue itself, but this required an explicit counter to be maintained, and things could probably be done in a much simpler manner. So how is the condition finally computed? It's computed as follows. So there is a counter called shed tick, which is incremented every time a new runnable coroutine is found and subsequently executed. So whenever shed tick is a multiple of this constant 61, you poll the global run queue. Why 61? Firstly, it's not too big, meaning that you don't want to poll the global run queue too infrequently. And if you poll it too infrequently, you have the same fairness and starvation issue. If it's too small, you end up polling it too frequently, and then you have the same lock contention issue and also fairness issue as well, meaning that you are not being fair to the go routines in the local run queue. And most importantly, it's prime. And the reason that being prime is most important is as follows. So 61 is chosen also by keeping fairness in mind to some extent. And the reason for this is that when you have an application running, it's likely that the frequency at which the application calls into the scheduler or the scheduler is required to find a new runnable go routine, that frequency is likely to be something that is a power of 2 maybe, or 16 or 32 or something along those lines. But it's less likely, but not impossible, that the frequency is something like a prime number such as 61. And the reason that prime number here is important is because you want to try and minimize the interference between the frequency at which the scheduler is called into and the frequency at which the global run queue is checked. Because if these two frequencies are even somewhat similar, what's going to end up happening is that that particular check is going to be true more and more often, and that leads to bad fairness as well as high lock contention. To illustrate this, let's consider the following graph. You have the orange line here being a frequency of 8, that is the application frequency at which it calls into the scheduler, and the blue line is of frequency 61 and the red line is of frequency 64. So as you can see, the orange line and the red line are zero together significantly more number of times than the orange line and the blue line are zero together. So you're essentially trying to minimize the number of collisions as much as possible. And another great way to look at it is trying to select the size of a hash map, and hence you choose a prime number over something like 64 or another power of 2, or 32, which isn't a power of 2, but you still might end up having more number of collisions there. So we've seen how go routines effectively end up running on threads, but what happens when they get blocked on system calls? If you have a go routine blocked on system call, there is effectively nothing that is there to run the other go routines in the processor's local run queue. There is still work to do, but there's nothing there to do it. There are resources elsewhere available, but we are not making use of that. The show must go on. So what we do end up doing is we perform something known as handoff to deal with this. Meaning we first disassociate the processor and the thread blocked in the system call state by issuing a call called release p, which disassociates these two. Now you have the thread, you get another thread, which is either already available for you, or you create a new one and you associate that with the processor. And now you have a thread to run go routines. You pick a go routine from your local run queue. If you don't have a go routine from your local run queue, you pick a go routine from your global run queue and start execution. Handoff can get expensive mainly because When you disassociate a processor and the thread and you try and get a new thread, what might happen is an existing thread might not be available for you, so you have to create a new one. And creation of this new thread can get expensive, especially if you have repeated system calls that might cause your thread to block. And the way that the Go scheduler tries and optimizes the survey is as follows. So the Go scheduler will do an immediate handoff only if it knows that the call is going to be blocking and for a prolonged period of time. One such example for this is a CGO call, for example, or if you do a system call such as read on Darwin architecture. In other cases, it's going to let the thread be in the block state and it's going to change the status of the processor to reflect that it is in a system call. If the system call returns soon enough, you don't have to worry about creating a new thread or getting a new thread, and all of that you can resume execution as is. But it's also possible that thread that you optimistically hoped for returning from a system call soon enough, it might not, can prolong for a long period of time. So in that case, sysmon comes to a rescue again. So sysmon sees that if a processor is in a system call state for a long prolonged period of time, sysmon is what is going to initiate the handoff then. So it's going to call release p and then handoff is going to happen. So that was when you enter a syscall. But what happens when you actually return back from a system call? So the scheduler tries to schedule this Go routine on its old P itself, the one it was on before going into the system call. So this is mainly to try and maintain as much locality as possible, and also to try and utilize that um, LIFO buffer if it could. The blocking and unblocking ping pong pattern can be done more efficiently. So if that is not possible, it tries to get an idle P and schedule it on there. An idle processor is something that ran out of work, didn't find work locally, didn't find work globally, didn't find work on the netpolar, didn't find work on another processor as well. If that is also not available, the scheduler puts this Go routine in the global run queue for some other processor to take it up. Awesome. So we now have a fairly good idea about what happens under the hood. So all of this is taken care of by the runtime itself. Are there any knobs that we as a user or a developer can try to use to control some of this runtime behavior? There are a few runtime APIs that are exposed, but it's always a good idea to first treat the runtime as a black box as much as possible, and only use these APIs only when it's actually and absolutely necessary. So a few runtime APIs that are available to interact with the scheduler are as follows. So the num go routine API, as the name suggests, returns the number of go routines that exist in your program at the time that it was called. And the remaining Go routines I would like to talk about just a little bit more in detail. So Gomax prox, as the name suggests, sets the value of Gomax prox. One thing to keep in mind here is that if this is changed after the program is started or while the program is executed, rather, for whatever reason you need to change it, keep in mind that it will lead to a stop the world operation, because the scheduler will have to resize the size of the list that holds all of the processors to be equal to the new Gomax prox value, and then subsequently resume execution. So a stop the world operation will occur there. Go shed API yields the processor that and the calling go routine gets put back into the global queue. If you plan to use it for performance reasons, it's likely that the improvement can be done in your implementation itself somehow. So use it only if it's absolutely necessary. Go exit, it terminates only the calling go routine. And when I say only, what I mean is if you call go exit on the main go routine, the other go routines are not going to, but once they finish execution and they come back, there is nothing to return to at all. Runtime detects this as a deadlock, and your program is going to end up crashing. And this one such example of where this is useful and used is in the testing package in the fatal method. One of the more interesting ones is lock OS thread and unlock OS thread. What this call does is it wires the go routine to the underlying OS thread, and it's mainly used when the go routine changes the underlying thread state in some form. So let's say it changed the thread state, and thread created a new this thread created a new thread, mainly because when uh, in the scheduler, if it sees that all the available threads are in a block system call state, right before the last thread enters a system call, it's going to create a new thread, so as to make sure that progress in work continues to happen and there's one thread that is always available to actively execute code. So let's say this thread creates a new thread, but this thread has no idea that the thread state was changed, and now this Goroutine is scheduled on this thread. It's not going to function as you might expect it to, and debugging this can get really really difficult. So whenever you have such a situation, try and use lock OS thread and unlock OS thread there. So Weaveworks actually has a really excellent case study on this. The issue they ran into was because they changed the underlying thread state in terms of setting a namespace. And these are the two related articles for that particular case study. I'd highly recommend going through them. This particular call, that is lock OS thread, acts like a taint indicating the thread state was changed, meaning that no go routine can now be scheduled onto this thread which is locked, and no thread can be created also from this log thread to try and avoid the issues that we saw earlier. And one caveat to keep in mind here, or one gotcha rather, is that if a go routine that has logged onto a thread creates another go routine, this created go routine, there are no guarantees that it's going to run on this logged thread. So don't create a new go routine when you expect it to run on the changed thread state. Okay, that was a lot of information, but it was really interesting to talk about as well. So thank you so much for sticking around and listening and attending this talk. So in conclusion, the Go scheduler is distributed and not centralized. Fairness is kept at the forefront of the design next to scalability. The scheduler design factors in domain-specific knowledge as well as language-specific patterns. Understanding runtime APIs well before using them, and use them only if it's necessary, and be especially careful if your go routine intends to change the underlying thread state in some form. These are a few references that were really helpful to me, and I hope it helps you as well. Thank you so much for listening, and I hope you have a great rest of the conference.